I think it's time to start today's final session. The speaker is Nikolay Abrosimov from Novosibirsk State University. He is going to talk about the volume of a hyperbolic tetrahedron with a right angle and one vertex. Please start.
Thank you very much for the introduction. And first of all, I would like to thank all the participants for attending this conference. And thank you for coming for my talk. It will be devoted to the classical problem of hyperbolic geometry, which is related to the theory of three manifolds and knot theory as well. Namely, I will speak about the volume of a hyperbolic tetrahedron with right angles at one vertex. The main result is based on our joint work with my student Stepan Stepanischev, and it is quite recent result, not published yet. So the calculation of the volume of a polyhedron in three-dimensional space of constant curvature is a very old and difficult problem. The first known result in this direction belongs to Tartaglia, who described an algorithm for calculating the height of a Euclidean tetrahedron with some concrete length of its edges. And the formula which expresses the volume of an Euclidean tetrahedron in terms of its edge length was given by Euler. More precisely, let T be an Euclidean tetrahedron with edge length dij between vertices I and j. Then its volume is given by the formula, by the following formula. Here we see that V is a root of some quadratic equation whose coefficients are integer polynomials in terms of edge lengths. The problem of calculating volumes of polyhedra remains relevant nowadays. This is partly due to the fact that the volume of a fundamental polyhedron is a main geometrical invariant for a hyperbolic three-manifold. And since Mostov-Prasad rigidity theorem, it is a topological invariant also. Well, every three-manifold can be presented by a fundamental polyhedron. That means we can pairwise identify the faces of some polyhedron to construct a three-manifold. Thus, the volume of three-manifold is the volume of its fundamental polyhedron. And for further consideration, we will use the upper half-space model of the hyperbolic three-space. So we denote by H3 a three-dimensional hyperbolic space, also known as Lobachevsky, Bolyai, Gauss space. And it can be modeled in the real three-dimensional upper half space with coordinates x, y, and t, where t is positive, and endowed with the metric s, given by this expression. Therefore, the volume element dV is given by this simple formula. The boundary of H3 of upper half space model is called absolute and consists of all points at infinity. And due to this definition, we have the following picture for geodesic lines and planes in the upper half space model of hyperbolic three space. Namely, the geodesic lines looks like Euclidean semicircles orthogonal to the absolute, and Euclidean half lines orthogonal to the absolute as well. And geodesic planes looks like Euclidean semi-spheres orthogonal to the absolute, and Euclidean half planes orthogonal to the absolute as well. A compact hyperbolic tetrahedron is a convex hull of 4 points in the hyperbolic space. These points are called vertices of a tetrahedron, and of course, here the convex hull is in the sense of hyperbolic metric. Let us denote the vertices of T by numbers 1, 2, 3, and 4. Then denote by Lij the lengths of the edge connecting vertices I and j. We put theta ij for the diagonal angles along the corresponding edge. And the diagram matrix G over tetrahedron T is defined as follows. It consists of minus cosines of diagonal angles. And also we can define so-called edge matrix of a hyperbolic tetrahedron T as follows. It consists of hyperbolic cosines of edge lengths. And it is well known that a hyperbolic tetrahedron T is uniquely defined up to isometry either by the set of its diagonal angles or the set of its 6 edge lengths. This is unlikely to Euclidean case where only the set of edge lengths defines the tetrahedron up to isometry, but the set of diagonal angles defines a Euclidean tetrahedron only up to similitude. It is a very difficult problem indeed to find the exact volume formulas for hyperbolic polyhedra of a prescribed combinatorial type. It was done only for hyperbolic tetrahedron of general type, but even for general hyperbolic octahedron, it is an open problem. Nevertheless, if we know that the polyhedron has a symmetry, then the volume calculation is essentially simplified. Firstly, this effect was shown by Lobachevsky. He found the volume of an ideal tetrahedron which is symmetric by definition. So ideal tetrahedron is a hyperbolic tetrahedron with all 4 vertices at infinity. And by this definition, it follows from this definition that the opposite edges, opposite edge lengths are equal to each other, as well as opposite diagonal angles are equal to each other. Moreover, the sum of diagonal angles a plus b plus c is equal to pi. So in fact, the set of all ideal tetrahedra forms a 2-parameter family. And as I said before, the volume of an ideal tetrahedron was found by Lobachevsky, and Milner find a very simple and elegant formula for this case. The volume here is just the sum of 3 Lobachevsky functions in diagonal angles A, B, and C. More complicated case with only one vertex at infinity was investigated by Winberg in 1993. The next very important particular case of hyperbolic tetrahedron. So consider a so-called hyperbolic orthoscheme. That is a compact hyperbolic tetrahedron with 3 diagonal angles equals to A, B, and C. And the remaining 3 diagonal angles are pi over 2. So this guy has 3 diagonal angles along 3 consistent edges equal to pi over 2. The volume of hyperbolic orthoscheme was independently defined by Lobachevsky and Janusz Balyai, from different points of view. But very nice exposition of the Lobachevsky formula was given by Coxter in 1936 in terms of so-called Schläfli function. And the Schläfli function is defined here on this slide. So let me continue. despite of the above mentioned very important but still partial results, a volume formula for arbitrary hyperbolic tetrahedron has been unknown until recently. The general algorithm for obtaining such a formula was indicated by Xiang in 1988, and the complete solution of the problem was given by Cho and Kim in 1999. Another formula from another method was obtained by Murakami and Yana in 2001. And then Ushijima found a geometrical proof for Murakami-Yana formula, which is also covered in the case of truncated tetrahedron. In these papers, the volume of the hyperbolic tetrahedron is expressed as an analytic formula involving 16 logarithmic Lobachevsky functions, whose arguments depend on the diagonal angles of the tetrahedron and on some additional complex parameter. So here is a Lobachevsky function, and the next theorem presents a Murakami-Yana formula for the volume of a hyperbolic tetrahedron, but I don't describe here the parameters, the complex parameters Z, Z1, and Z2, because it would be too long and took more than 2 slides, I think. Dmitry Derevnin and Alexander Mednych in 2005 presented another closed integral formula for the volume of a hyperbolic tetrahedron, and it is shown on this slide. Again, it expresses the volume in terms of diagonal angles. Here is a detailed explanation how to find the limits of the integration in the Derevnin-Mednych formula. It was surprising when we found that more than 100 years ago, Italian mathematician Sforza already found the formula for the volume of hyperbolic tetrahedron of general type. That is a very nice formula indeed. So here we assume that all the diagonal angles are fixed except theta 3,4, which serves as a formal variable. Then the volume is given by this formula, and again here C34 is a 3,4 cofactor of the Gram matrix G, and we consider C34 and G itself as a function in one variable theta 3,4 denoted by T. T is a variable of integration. So the original formula was published by Sforza in Italian in 1907. And the new comparatively simple proof of this formula is published in our joint paper with Alexander Mednych. The new proof is based on Schläfli differential equation and also using Jacobi equation, which relates the minors of square matrices. Here is all the above mentioned formulas expressing the volume in terms of diagonal angles, and here is the existence theorem for a hyperbolic tetrahedron in terms of edge lengths. And this is a volume formula. The next theorem, this theorem, can be considered as an analog of Sforza formula, but in terms of edge matrix, of the edge matrix of a hyperbolic tetrahedron instead of its Gram matrix. So this is our recent joint work with my former PhD student, Bao Guong. It was published last year. So on this slide, I collect all the above mentioned formulas. And as you remember, formulas for general hyperbolic tetrahedron looks very complicated. But the formulas for particular cases are rather simple. So the natural question arises, can we find a comparatively simple formula, but for a relatively wide family of hyperbolic tetrahedra? And we decided to consider the following three-parameter family of hyperbolic tetrahedra, namely a hyperbolic tetrahedron with right angles at one vertex. So it has three edges adjacent to one vertex V4 on this picture, adjacent to one vertex, which are pairwise orthogonal to each other. And it is convenient to determine this hyperbolic tetrahedron in terms of the lengths of these three pairwise orthogonal edges. So we call the lengths, we denote the lengths L1, L2, and L3. And without loss of generality, we can consider such a tetrahedron in so-called standard position in the upper half space model. That means that one vertex V4 has the coordinates 0, 0, 1. The vertex V3 lies on the coordinate axis, vertical one, and the remaining two vertices V1 and V2 are lying on the coordinate planes. This makes our calculation easier, but we still don't lose the generality as well. This family of hyperbolic tetrahedra was previously raised in PhD thesis by Galia Bayganakova in 2012, where she found trigonometrical relations between the diagonal angles and lengths of the edges of such a tetrahedron. Also, if we consider this picture, we can apply mirror reflections in three pairwise orthogonal faces of this tetrahedron. Then what we get is a hyperbolic octahedron with so-called MMM symmetry. And the volume of such a hyperbolic octahedron was given in our joint paper with Galia Bayganakova in 2013, but in terms of diagonal angles. And now we produce a rather simple formula in terms of edge lengths for such a hyperbolic tetrahedron, which can be considered as 1/8 part of corresponding octahedron. Also, I would like to note that Falco-Lanner proved that there are exactly 9 compact Coxeter tetrahedra in the hyperbolic 3 space, and one of them with such a set of diagonal angles is representative of our family of tetrahedra under consideration. And the remaining 8 Coxeter hyperbolic tetrahedra are hyperbolic orthoschemes. So this is the main result. Let T be a hyperbolic tetrahedron given by the length L1, L2, L3 of its three pairwise orthogonal edges adjacent to one vertex. Then the volume V of T is given by this simple formula. Here, x0 and y0 are nothing more but coordinates of the center of the hyperplane defining the upper face of the tetrahedron in the standard position. And of course, when we obtain any new volume formula for some hyperbolic polyhedron, we need to double check it using some previously known results. So for the particular case, we consider one parameter subfamily of our three parameter family. We put L1, L2, and L3 equal to L and consider this one parameter subfamily of hyperbolic tetrahedra. Then we use above mentioned general formulas for the volume of hyperbolic tetrahedron. So we use actually two previously known general formulas, and the third column in this table is for the new formula. And you see that the results of computation coincide to each other in all three cases. And when we made this verification, we figured out that the new formula works very well indeed. I mean, for it is convenient for computation on the computer, and it works very well even for large values of L. So it allows us to analyze the behavior of the volume function, as well as its asymptotic. So as L attends to infinity, the volume V of T attends to 1/2 of so-called Catalan's constant. That is 1/8 of the volume of regular ideal octahedron, which is a well-known constant in the theory of three-dimensional manifolds. For example, because the regular ideal octahedron can serve as a fundamental polyhedron for the complement of the Whitehead link. And then we find the normalized volume. So we were motivated by the paper of Nimul and Membrati, 2018, where the authors find the normalized volume of a compact regular hyperbolic tetrahedron. So let us find it for three-parameter family of tetrahedra under consideration. We denote by X, Y, Z, and W capitals the faces areas of a hyperbolic tetrahedron with right angles at one vertex, and we compute the areas of each face. So we find X, Y, and Z using the analog of Heron's formula for the area of hyperbolic triangle, known as Blinsky formula. And to get the area W, we use a generalization of the hyperbolic cosine rule for the faces of tetrahedron given by McConnell. He is one of the developers of Wolfram Mathematica and known enthusiasts of the hyperbolic geometry. Thus, we get the normalized volume nu of tetrahedron T, which is as follows, where V is hyperbolic volume and S capital is surface area of a hyperbolic tetrahedron. And again, considering one parameter subfamily of our tetrahedra, we can draw a graph of the normalized volume nu in terms of length L. And here we see that as L is increasing, the normalized volume is monotonically decreasing. And again, we can find the asymptotics, and as L attends to infinity, the normalized volume nu attends to this constant. So thank you very much for your attention.
Thank you, Professor Nikolay. Are there any questions or comments? I have one just curious questions. Would you show me the page 2 again?
Page 2?
Yeah.
This one.
Yeah, okay, yeah, this page. There is the number 288 in this matrix.
This number.
Yeah.
Mm-hmm.
So do you have any meaning of this number?
Well, there is a generalization for higher dimensions of this formula for the volume of Euclidean simplex. And the constant here on the left depends on the dimension of the space.
Okay, thank you.
And it increases very, very fast.